We're now going to look at something called homolytic bond dissociation energies. So I need to introduce some basic terminology here. Homolysis or homolysis refers to breaking a covalent bond into two halves. Since a covalent bond is two shared electrons, if we break it into two halves equally, where each atom takes one electron, so they just basically take back the electron they had shared, that's called homolysis, okay? And the reaction for that would look like this that I've written down here. These are just supposed to be two generic species on either side of the double bond. Choosing B here is probably not a great idea because there is actually an element B, right? Boron, but that is not intended to be the element boron. That's just intended to be some species B. If we break that bond homolytically, if we imagine that this bond is this pair of electrons written not as a dash, the way we have been writing bonds, but written as the actual two electrons shared between, homolysis would involve separating these. One of the species would get one electron, the other species would get another electron. It turns out then, in theory, if we could do this reaction, we could measure the amount of energy that it would take that we would have to put in order to break this bond. That would actually be delta H for the reaction. How much effort do we have to put in to break that bond? And there are ways to sort of measure this. And these then are called the bond dissociation energy, because it's basically the bond just dissociating or separating apart. The bond dissociation energy is often abbreviated BDE. And there are, in fact, several different bond dissociation energies for a given bond, because you can break it apart homolytically, but you can also break bonds apart heterolytically, where one of the atoms takes two electrons and the other takes none. We saw this, for example, in the first step of the SN1 and E1 reactions. We're going to focus on homolytic bond dissociation energies. Homolytic bond dissociation energies are in many ways much more useful because they generally are not affected by the solvent, whereas heterolytic bond dissociation energies change depending on the solvent, because once you separate those species and they become charged, then the solvent interacts and changes delta G, changes delta H. Now, when we look at bond dissociation energy, then it turns out if that's a delta H for that reaction, then the sign of delta H is either going to be positive or negative. And in fact, there's a rule when you work with delta H of reactions. If you have a reaction, you know it's delta H in one direction. If you turn the reaction around so that the products become the reactants become the products, that reverse reaction will have the same delta H, but it will be the exact opposite sign. And it has to be that way, or else we could make perpetual motion machines. Okay. So what we find then is it takes effort. We have to put energy, potential energy, into the bond in order to break it. So breaking bonds increases the potential energy as we go from reactant to product. And in that case, when you increase the potential energy within that system, the amount of energy is going up and delta H is positive. Forming bonds, in other words, the opposite direction, turns out delta H is going to be negative. So in general, we don't write on our tables both directions. We just write one direction, then we just change the sign depending on how we are using it. This is a table of bond dissociation energies, basically roughly similar to the one in our particular textbook. This will be our table that we are going to use. And in fact, I will be posting this as just out of the notes, but a separate page as a reference sheet. Now, I need to talk to you about the numbers on here and how this table works. So the first thing I want to point out is the units for the bond dissociation energies. It turns out that organic chemists, generally work in energy units of kilocalories per mole. Now, that is not really the modern SI unit that's used really in most other fields, such as physics, even physical chemistry, stuff like that. When you guys were working with energy in general chemistry, you generally worked with joules and kilojoules. And there's nothing necessarily wrong with joules. And in fact, you can multiply by a factor slightly larger than 4 to convert from kilocalories to joules. The problem for organic chemists, at least old ones like me, is that we actually have a lot of these numbers memorized because they're very useful benchmarks for certain things that allow us to just kind of make really quick off-the-cuff predictions. But we have them memorized in kilocalories. So most organic chemists still really work in kilocalories per mole. As a result, what I did was I took the table from the book, which is actually in kilojoules. I think it might actually have both columns. Took the kilojoules column out, or the joules column out, and only have kilocalories in it. And those are the numbers we're going to work with. Now, you are not going to be required to memorize this table. This table will be provided for you on exams or in any circumstance when you would need to use it. And in fact, I wouldn't memorize this table. I don't think that's super useful. Although there are a few numbers, if we work with them a few times, you may get a rough idea of what they are. Now, the way that this table works is we have various species on here. I don't know if you can see all of these, but we have various species. Some are just diatomic, like hydrogen. In a diatomic species, it's very obvious which bond you would be breaking. So for example, here's hydrogen to hydrogen. There are no other bonds. The bond that would be dissociating would be this hydrogen-hydrogen bond. And by the way, here's our bond dissociation energy, 104 kilocalories per mole. You're going to see by looking at the numbers, that's a pretty big number, one of the largest. There's a lot of potential energy in that hydrogen-hydrogen bond. So that's one type. However, there are also polyatomic species. So I'm just going to look at methyl, but then I'll show you a couple others. So if we look at methyl, methyl is actually CH4. But if we look at one of the carbon to hydrogen bonds, there would be a hydrogen on one side, and then there would be CH3 on the other side. And so on the table, to indicate that we're breaking that carbon to hydrogen bond, what they've done is they've put CH3 on one side, a large dash, that's the bond that's being broken, and then a hydrogen on the other side. The significance of that then is important when we look at ethane. So here is ethane, carbon to hydrogen bond. So ethane is CH3, CH3. In ethane, there are two different bonds, different bonds of different sort of composition that could be broken. One would be the 6 carbon to hydrogen bonds. The other one would be the central carbon to carbon bond. To indicate that we want to break the carbon to hydrogen bond, can you see they put ethyl group on one side, a dash, and then a hydrogen. This would be the ethane carbon to hydrogen bond. Right next to it, if you look, here is methyl group to methyl group with a dash in between them. This would be the carbon to carbon bond. You can see that the numbers are different. It's very important that you know which bond you are breaking and which bond that is on the table so that you can get the correct number. This is even more complicated. You can see that the table was sort of written in a fully condensed format to make space. So here, what we have is CH3 connected to CH2, connected to another CH3. So that's propane. And what we're looking at right here is a carbon to hydrogen bond on the middle of the 3 carbons. So this group would become basically isopropyl with a radical in the middle and then a hydrogen. And similarly, this would be tert-butyl with a radical on it, hydrogen radical. Then there's a couple other bonds. Some of these are not on the table in our book, but I went and looked them up. So for example, a methyl, which has a phenyl group attached in place of one of the hydrogens. In that case, then, we would call this a benzylic carbon. It's a carbon directly attached to a phenyl group. And those benzylic carbons are unique. They have resonance stabilization of the radical. They have a different number. Here's an allylic. Remember the allyl group where you have a carbon directly adjacent to a double bond, not part of the double bond. That has a unique number. This is vinylic. This is a carbon directly of the double bond and a hydrogen directly attached to the double bond so that we get a vinyl group right here. That has a different number. And then finally, this is a phenyl group, one of the hydrogens on a benzene ring, for example, breaking there. And that's a different number. You see there's a big difference in these numbers.